Anna, will you? Okay, welcome everyone to today's colloquium. We are very happy to have Simon Caron-Huot today from Montreal, who will talk about gravity and causality. So we're very happy to have you here, and please go ahead.
Yeah, hi everyone. It's a pleasure to speak with you remotely. Let me share my screen. Yes. Yeah, so I'm going to be talking about a project which has been going on for some time and with various co-authors. And we're just trying to understand basically the fact that Einstein gravity works so well. That's something we see over and over again in experiments, just to show two famous plots that I will not describe. But the basic question is, when we say that we're testing general relativity, like as a theorist, you can ask, what are we really testing? And we understand that a lot of the structure is forced on us by basic principle like causality and unitarity. And what we try to do in this talk is try to understand just how much quantitatively, how different could gravity be different from Einstein if we stick to those basic principles. Okay. I'm going to try to extract quantitative predictions of these things. The general framework we have in mind is a kind of effective field theory framework where we're going to assume that the modifications are suppressed by a scale which is not the Planck scale. Because if it's suppressed by the Planck scale, then forget it. Observationally, you're going to see it in your lifetime. So let's hope that we have some kind of correction we can see, and then it's going to be associated with some scale which is below the Planck scale. And the scale could be above colliders, or actually it could even be below, as we'll discuss later in this talk. I'm going to distinguish two different length scales. It's going to be just introducing concept that will be key, is that modification of gravity would be associated with higher spin particles, like spin 4 and more. But there could be, say Kaiser-Klein modes or other massive spin 2 particles. They are not going to affect our analysis at all. So there's going to be a key scale, and we're going to try to understand what we can say about this scale. And we're assuming we do experiments below it. So we're interested in graviton scattering below that scale. And the idea is we can write it in some kind of a effective theory where you have a Lagrangian like this and some derivative expansion. Oops. And we'll be looking for effects that scale, that have this power law scaling, that, as I said, effects that are much bigger than you would get from a Planck suppression. Okay. We'll be looking for effects of this size. And then the question is, you may expect order 1 coefficients in front of these effects, and we're going to try to mathematically bound how big can these coefficients be. That's our goal, to upper bound these coefficients. This is trying to maximize some coefficients subject to some constraints at the general field called bootstrap. So we're going to be applying bootstrap ideas. I should also say that you can ask various extremization problems. One of them that's been very interesting recently is that you can also ask, if the coefficient were to come with a Planck scale, like how small can you be? So like how close to Einstein theory can you be? And it turns out that the closest thing really looks like a string theory. That was an interesting discovery by this guy. But we ask the opposite questions, like if we're looking for something we can observe in the sky, like how far from Einstein can we be? Okay. How big can this correction be? That's the question we ask. So here's the outline. I'm going to be reviewing kind of the general framework, how we think about modifications of gravity and so on. And I'm not going to give a laundry list of like the thousands of modifications that people have looked at, but like from our viewpoint, how do we think about it? And how it affects graviton scattering, and what does causality and unitarity, what these principles mean for graviton scattering. Then we'll discuss some known results that have been obtained by that. And then I will describe a bit more in detail the mathematical method we'll use, some kind of dispersion relations, and I will use it, and then I will flash some results. It's been a long thinking project, and it's actually going a bit outside of my comfort zone, because I mostly do things related to the strong force or bits of QCD and so on. So gravity is a bit outside my comfort zone. If I say something stupid, just shout. And yeah, there's been a long series of work since starting this project 2 years ago, and it's been an interesting interplay between conformal field theory approach to this, where you concern gravity in ADS versus flat space and alternating, and then this last iteration that don't worry, I'm not going to talk about 5 papers, but this last iteration is mostly about gravity in flat space. But this essentially parallel story in ADS curve space. Okay, and yeah, the main result is like to have some discussion of, we're going to show that modification of gravity requires some higher spin states, and then you can ask, like, are you forced to see them at colliders or not? And can you hide them, or do you have to see them? So this is still a very open question, but like kind of open a discussion on it at the end. So how do we think about concentration of gravity? So for us, we'll be thinking about scattering of gravitons, and we'll be scattering, well, imagine as a tough experiment that we're scattering gravitons at energies much less than a Planck scale. Okay, so they interact quickly with each other. Mostly they just pass through each other. like when you send 2 beams of light against each other, like they just pass through each other. That's what these gravitons do. But then they interact a little bit, and the first way they interact is by they deflect a little bit because of Einstein's theory, and that is predicted by this term. And then we're going to try to when you add these higher derivative corrections, you end up with other terms that we can see in this 2-to-2 scattering amplitude. Like you could have higher derivative correction at the vertices, which give a Riemann cube term would give something at the vertex, which give you something with a 1/t pole. You could also exchange like scalars. That will turn out not to matter, but you could do that. And you could also have a Riemann to the 4, which give you some contact interactions. And you can try to list index contractions between Riemann tensors. It's a bit painful, but the way we think about this is that all of the observable effects, they are, when you have contact interactions, they just give polynomial scattering amplitude, and it's actually very easy to enumerate polynomials. So as far as we're concerned, the higher derivative, all these index contractions of Riemann to the 4 and various derivatives acting on them, they're just a bunch of polynomials that affect the scattering amplitude. So that's how we think about modifications to gravity. And we're going to try to bound these coefficients that appear in this series. That's our goal. But there's a bunch of things that people refer to as modifications to GR that we're not going to bound. Perhaps a very popular thing that is considered by many people is what if you replace R by a function of R, like the Ricci scalar? And it turns out that this is a well-known fact, but not well, I didn't know it before I started this, but it's a, I don't know what that fact, any theory that's just f of R, you can actually write in terms of usual Einstein theory coupled to a minimally coupled scalar field. And then what the function you have is encoded in the potential of that scalar field. So as far as we're concerned, this has absolutely zero imprint on graviton scattering. And this I wouldn't call a modification of gravity. It's just like adding some scalar to your theory. It's just gravity with a different matter, okay? So this f of R gravity, we're not going to bound at all. And in our language, it's not even a modification to gravity. More generally, you can ask, if I go back one slide, you can ask, why did I start with, why did I start with Riemann cube? And what about R square or Riemann square and these things? And the point is that anything that involves the Ricci scalar is like an equation of motion. So in this derivative expansion, you can remove it order by order by field redefinition. So So there's no point in writing Ricci tensors. So all the other things you write in terms of Riemann. You can. This will be a non-trivial index interaction between three Riemann tensors. But at quadratic order, Riemann square is basically a plus combination of Ricci is topological invariant. So there really is nothing you can write down at second order. So the first non-trivial thing that affects observable scattering amplitudes is in the derivative expansion is Riemann cube. That's in 4 space-time dimensions. We're going to be focusing on 4 space-time dimensions. Okay. And also, yeah, as I mentioned, anything that involve interactions between scalars, generally these give interactions which don't, the defining feature of gravity for us is that it's a force that grows with energy. That's related to the spin, the graviton having spin 2. But yeah, when you exchange scalar or photons, you get forces which don't go with energy as fast. And basically, we're not going to say anything about other forces. So for us, the gravity is a force that goes with energy, and that's what we constrain. And also, there's a million of other things that people discuss, like torsion, or I don't know, if you don't have metric or whatever other formulations. But all of these, from our perspective, they just give you different ways of coupling the graviton, which is a spin 2 particle, to matter fields, which are smaller spin. Okay, and it's just so this is a question which is interesting of bounding how can gravity couple to matter and the size of non-minimal couplings. That's an extension of what we're going to be discussed today, but we'll not touch that. Okay. So what we do apply to any theory where you have a graviton that looks like a spin 2 particle that you can scatter. So and we see gravitational waves, so we know that we have that in the world basically. Okay. So we have a kind of general slide about the causality. So describing what our assumptions. It's just basic question is like, what has causality done for you recently? And if you're high energy physics, then a lot. So causality, I refer to the notion that signals cannot travel faster than light. And this notion is, this gets slide, I'm going to spend a few minutes on this slide, but it's, I'm going to say a few basic things and a few less basic things then, but like a basic thing that causality explains a lot of things in the world. Okay, basically, that's why it's important. The most basic thing that explains is why all forces in nature are mediated by waves. And this is something you can explain to a layperson. And the standard argument is that if you have an electric charge that, say in an antenna or an electric charge, then it exerts the force on other electric charges. So if you change the position of that charge, well, relativistic causality tells you that you cannot have instantaneous action at distance. So the force on some other detector charge will have to change after some time delay. But since the force changes, and force can give you energy and momentum, can transfer that, the information about the fact that the charge has moved must come with energy and momentum with it. And that is why, causality requires electromagnetic waves to exist. And by the same token, that basically why Einstein kind of had to know that there would be gravity waves even long before he had the field equations for that. Okay, so you can't have a force without having waves in it. That's a very basic thing, and that's why we do field theory. And when you add quantum mechanics, these units of this energy has to come in discrete units, and that's why we have particles. And a more refined argument of this that will actually come later is that causality also requires for you to have antiparticles, to have commutators vanish outside the dipole. And then, causality is a very successful principle. Very, very, its explanatory power is unequaled. The two aspects that I will play a role today are a bit less well known. So one aspect it's that causality also explains why effective field theory as a concept has to work. We'll explain what it means in a sharp sense. And it's also nicely explained where gravity has to be attractive. You have a force which grows with energy, it has to be attractive. So we're gonna these two aspects would play an important role. But that's like, yeah, it's just adding to the scorecard of gravity, of causality. Okay. Why do we assume it? So it's not like a religion, like it's successful, so you have to assume it. But like, well, first of all, there's very good experimental tests, and I'm going to go through various experimental tests. But like the basic framework of quantum field theory will not exist without this. Causality was not correct at some basic level. But that doesn't mean it's an exact property of nature. You know, it could be that causality is very good approximation, but somehow not exact. And one hint of that is that if you ask people who try to work on quantum gravity, I don't work on that, but if you ask people who work on this, they tell you that it's very difficult to define like bulk observers and what causality will mean for them. So the fact that it's hard to define what it exactly means suggests that maybe it's not a fundamentally exact notion. But more practically, the reason we're going to assume causality in this talk is that there's no real alternative. It's not like there's a scenario A, there's causality, scenario B, there's something else. This is just a slide to like provoke stuff. I would really like if there was some alternative theory to like a causal, some good model of a causality that could go out and test. I never saw. I'm not aware of any such model. And the basic point is that as soon as you give up on, as soon as you start allowing things like instantaneous action at the distance, then like you can write whatever you want. Like you know, if you want a theory of quantum gravity, here's a theory of quantum gravity. Like here's a Newtonian, this quantum, is gravity. What more you want? You can write whatever you want. But the problem is that it's too flexible, right? There's no. If as soon as you start allowing instantaneous action at distance, you can do whatever you want. There's no. You can't have a predictive framework. So I think it's a very some creative idea would be needed if indeed we need to give up causality is not an exact property. So we're going to assume today that's an exact property and see where it leads us. But I want to emphasize there really is no alternative to doing that. So there are some results that people have obtained that relate causality and gravity. One famous result is from the late Weinberg. We basically show that, well, with Lorentz invariance. So if you have a Lorentz invariance S matrix and you say words like you have a massless spin 2 particle in your spectrum, then automatically the interaction at long distances, the interaction between this particle and itself and with matter have to reproduce GR. That's a beautiful result. And essentially what we're going to try to do is look at the corrections to this result. Okay. So some of the corrections, there have been nice arguments in the past recent decades about controlling corrections to this. And here I will sketch one of those. It will come back later. One nice argument it's an argument that constrains these vertices. It's what you do is you look at the force. You look at scattering at large impact parameter between a graviton and some object, which could be a black hole or a particle or anything. So you scatter gravity against some object, and the long range force comes from exchanging gravitons in the channel. So long range force is affected by higher derivative corrections. You could put that as vertex. But this long range force determines whether the graviton has a time advance or a time delay as it goes through, as it passes through the object. And a well-known fact is that if you just have Einstein gravity, you only get time delays. Okay? Like gravity slows down the time it takes to go through some object. And that's because it's attractive, roughly speaking. And yeah, so we look at this. So gravity here occurs in this. So this scattering amplitude that controls that, and gravity shows up on the diagonal, and it's positive. And at relativistic frequency at relativistic energies, it's actually logarithmically divergent if you integrate the time delay. So it's very positive. But then when you add higher derivative corrections, it turns out that it's a bit subtle how to think about the time delay or advance, because you have different polarizations of your graviton. Like it has two different polarizations, and different polarizations can have B refringence. One of them could speed up and the other slow down. And what this author showed is that this is exactly what happens when you turn on these higher derivative corrections. And well, the eigenvalue of this matrix, you get, if this correction is too large, you're going to get a negative eigenvalue, and that's bad. So if you require that you can't see causality at impact parameters where you trust this diagram, you find that this diagram has to break down at some scale, which they argued would be just the mass of some new higher spin particles. But yeah, you get parametric bounds of this type that constrain the size of this coupling in terms of the mass of new physics, just from causality, and it has to do with this time advance business. And then there's some other kind of line of approach, which has been a bit disjoint, but it works well for constraining. It gives you typically sign constraints on contact interactions. I haven't done a contact diagram, but yeah, when you look at contact interactions, you can try to take forward limits and do integrals over the imaginary part of the forward amplitude. And the imaginary part of forward amplitude by the optical theorem is a positive cross-section. So when this kind of dispersion relation allow you to write coefficients of higher derivative terms as integral over something positive. So you get some interesting sign constraints on contact interactions. So the approach I would talk about, we'll be using, will somehow merge those two things. So and the main goal will be to convert, or to get bounds on everything, not just this coupling, but also the main goal will be to get rid of this squiggly thing and have an actual inequality with a number in it. So it's different between a sharp bound and just a wavy argument. That's our goal. Yeah, feel free to interrupt at any time. There's a few common complaints that I don't want to address. So let me spend not too much time on the slide, but like, I just want to mention them just so that you know that we're not worried about those things. And if you're worried, you can come and ask about, like, S matrix doesn't exist because of infrared divergence, and that leads this log that we talk about. But as far as I understand, this log in the scattering phase is a very simple physical origin, and you can understand it from using it in physics. And if you have a framework where you can get rid of these higher divergences by looking at finite amplitudes, I think it's just going to make our bound stronger. So that would be nice. And the other thing is that why we're going to be studying graviton in flat space and flat space scattering. And the idea is that we're using there's a causal structure in a synthetic flat space, causal structure at infinity that we're going to be using. That's important for us. Then you can ask, well, we live in an expanding universe, so why do we care about, there's no asymptotic states, well, why do we care about S matrix? And, basically is the point is that, probably the effect of space-time curvature are very small, should be suppressed by the expansion rate compared to the, and we assume that this is much less than this higher spin rate scale you're looking for. So, basically for the same reason that you can compute LHC cross sections without thinking about the curvature of the universe, we think that
I should say, if I may, that if we are so strict, then we can conclude quantum field theory doesn't exist.
Yeah, exactly. So I think at this level, with the standard of rigor, like, we can't do particle physics, right? So
no, nothing exists because Landau pole, because of, in addition to what you list, there are many reasons why the quantum physics doesn't work. Actually, what I was, excuse me, I jumped in this.
No, good.
I was thinking that eventually with this kind of methods, you will rediscover string theory in some background, which is a flat background. if you continue.
Oh, you mean string theory? Oh.
Right, because you want to have something
yeah,
consistent for a gravity, and then you start with spin 2 particle scattering, or you will discover something that we don't know, and it's surprising because we thought that string theory is unique.
Yeah, this is exactly the kind of goal here, because we, you might hope that the outcome, but I'm gonna stick about the outcome. It could be the outcome is like the only possibility is string theory, or it could be that there's something else that comes out. So right now, the sort of bound that we get some allowed region, and then in the middle of it, the string theory somewhere. So it's not like it's not like string theory is the only option at the moment. But
that's what I was wondering. I mean, do you guys manage?
No, we're not narrowing down around string theory.
Oh, okay.
But and there are some features that are qualitatively distinct that are going to remain allowed. So that's interesting. But I mean, this is in progress also. Like you keep adding constraints, and you eventually reduce every time you exclude something, it's excluded forever. But there are many things to exclude.
Yes, but someone like me would say that if you discover something nearby, I would say that's a string theory in a slightly different background.
Yeah, we discuss some things that are qualitatively different. But yeah. And the last thing in this kind of long introduction, the last thing I would like to emphasize is the last thing, something I mentioned at the beginning, is that what's going to drive this correction to GR are higher spin particles, not spin 2, but really higher spin, which could be string states, but don't have to be stringy modes. They don't have to be stringy modes. And the basic reason that spin 2 states don't matter is that, well, first of all, they're ubiquitous. One way they naturalize if you have some compactification. But if you think about this framework of compactification, the things that are going to matter to us are the things that couple to a pair of massless gravitons, because that's what we're scattering. And then if we can produce this AV spin 4 particle from 2 graviton state, then it can affect it can cause a correction to GR. But it's easy to see that in Kelser-Klein reductions, the Kelser-Klein gravitons or Kelser-Klein particles don't decay to 2 gravitons. And that's just because some orthogonality relation of wave function, because the massive gravitons are like a wave function that's 1, and then you integrate against this, you get 0. So even if Kelser-Klein modes exist, like they don't naturally decay to 2 gravitons. We don't expect to see them in graviton scattering. So that's the basic physics reason why our bounds are not going to be sensitive to that. But that's just something we anticipate. It's just, we don't have to put that in. It's something that comes out of our analysis. Okay, but that's physically why it's the higher spin guys that are important. This could be like this other excited states in this rigid trajectory of the graviton. So, and one last thing also. It's important to set scales here, because actually the options are a bit when you leave the string theory framework, the options are a bit quite wide open. Like and what I just put in blue here different length scales that you might thinking about for testing corrections to GR. And for example, at LHC, we kind of know from LHC that any scenario that looks like string theory, the string scale must be above like several TVs, the scale of probe at LHC. And the basic reason is that string theory doesn't just predict corrections to gravity, it also predicts that all matter have KK modes. So if you scatter quarks and gluons, you're going to create KK modes of them. That's not KK modes, sorry, but stringy excitations of the quark or stringy excitations of the gluon. And these have couplings are not suppressed by Planck, so we just have to see them. If the string scale were that low, we would have seen them in the scenario. But if you exit the scenario and ask yourself, can you have some higher spin state that coupled to gravity but not to matter? Maybe it's not possible. But if you contemplate this, then you can have a higher spin scale that's much lower than the standard model scale. And then, this is in fact, when people do experiments testing general relativity in the sky, the sort of scales that are probe are more like 10 to the minus 10 electron volt point. It's like kilometer, a microscopic object is like kilometer size. It's completely different order of magnitude scales that they are probing. And then you can also ask about experiments that probe gravity at like tabletop experiments, and then this probes some other energy scale. But these are not technically modifications to gravity in our language, because you could always get a fifth force that have some like Yukawa type potential that by Famish energizing scalars, and this, and because it doesn't grow with energy, the thing that we call gravity for us are things which grow with energy, forces that grow with energy, not static forces. But yeah, they are still probing these scales. So it's actually not, as far as I know, it like there's no invariant. There is no. There's no model-independent constraint that tells us that these higher spin states have to be above the collider physics scale. But one general question that I think is very interesting is like, we do collider constraints, and in various scenarios like string theory, this gives us very strong constraints on new physics scale. But like in the model-independent way, what do we really know about the interpretation collider and these other setups? And I'm not going to answer this. I think it's an important question. If we're ruling things out from colliders, then like what are we really testing from testing GR in the sky? I think we're testing causality still, but yeah, it's important to understand what we're testing. So yeah, so that's kind of question. Just to make sure we're all of the same mindset. Like, do we really know that we can't have higher spin particles with 10 minus 10 eV? Maybe we do, but I'm not sure we know. So like, are we really sure? Yeah. So here's the method we're going to use. Give you some things of content. So we studied 2-to-2 scattering of gravitons. And this is a space-time diagram, roughly. And I just want to make a statement of what this causality means. If you think about causality, you might think that causality has to do with, okay, you collide things, they hit at a point, and then the things that come out have to be in the future like cone of that point. That's not correct, because that point only exists in your head, in your mind. There's no physical point where interactions don't happen at point. So, and in fact, if you scatter extended object, it can bounce off each other and come out earlier than if they had it at a point. So causality actually doesn't tell you anything about fixed angle scattering, that I know. Causality, however, tells you something about forward scattering, because if you create an excitation by measuring the gravitational field here at this point 1, and in the forward direction, there's a real chance that you spill outside the future light cone of point 1. Okay, so in the forward direction, you can actually test this notion that measurements space-like commute, but you can only test this in the forward direction, because all of these points here in fixed angle scattering, they're in the future light cone of point 1. You don't expect them to commute. There's no causality constraints there. Causality is about the forward limits. That's why this rigid limit is so important in this business. And the other thing is that you might have thought that causality is about particle 1 not coming into faster than light at this point 3, but this is a bit subtle because particles are waves. So like, what is exactly the arrival time? It's not, you can have causal wave propagation even if the group velocity is faster than light. Waves do weird things. And the strongest statement of causality is not about like particles and times. It's really about waves, and the wave, and if you have scatter waves, you really don't have control over positive energy versus negative energy. So it involves antiparticles. And the physics picture is that if you try to do an asymptotic measurement at point 1 and point 3 that are space-like separated, you're going to have an amplitude from particle 1 going from particle 3 that has to cancel against an antiparticle going from 3 to 1. And the statement that these two things cancel is crossing symmetry. So the amplitude have to be related. And you need an LST in upper alpha energy plane, and they have to be related by anti-conservation. But crossing symmetry is the strongest possible statement of causality. That's what we're going to use. So how do we use it? So we consider scattering amplitude. S is like center of mass energy square. So we consider scattering amplitude. What am I writing here? Does it? I have too many Zoom windows. Yeah, it's causal. Yeah, we assume that what we're going to assume is that at high energies, we don't know what the amplitude is, but we assume that the scattering remains causal and unitary at all energies. That buys us an elasticity on the upper half plane. At least outside some low energy region, that's not going to be relevant anyway. So it can be weird things happening in the middle. We don't care. So we need an elasticity and far away in the upper half plane. And our minimal axioms, I'm going to try to state them very precisely. It's a bit technical, but I want to state them because they're a bit weaker than what many people assume in this business. Our minimal axioms is that we assume that the scattering amplitude is analytic outside these blue arcs. And this blue arcs here is basically this is the EFT cutoff. This is the so the scale here is set by the EFT cutoff scale. Okay, that would be the higher spin scale. So we assume that the amplitude is analytic outside this blue curve. That's what is written here. And the other assumption, which is really just basic, really just S dagger S equal 1, is that if you scatter normalized wave packets, then scattering amplitude can't exceed its normalization. So when you look at this concept of smear amplitude, it's going to be useful later. It's just a notion of a normalizable wave packet. If you scatter things that have normalizable wave packets, the amplitude can't grow, and that gives you this boundedness property. It's a boundedness property that's trivially holds in the real axis. The thing which is less obvious that but basically if the amplitude doesn't grow like exponentially, like crazy in the upper half plane, then a function that is bounded on the real axis is automatically bounded on the whole upper half plane. And that's going to allow us to neglect some arcs at infinity. So we assume that this boundedness property holds all along the upper half plane. But as I said, the only assumption here really is that it doesn't grow exponentially. Then it's if it doesn't grow exponentially, it's thematically bounded by some version of the maximum principle. And this, it's an axiom you can question in quantum gravity. People have questioned it, but I think we have strong support from it in this paper where we study ADS gravity. So all of some rules we derive from this type of argument are rigorously valid in theories for quantum gravity in ADS. So I think there's no indication that, I think there's really no indication that gravity modifies this. So we need an elasticity and boundedness. And once you have these two things, you get dispersion relations like Cramer's Crony type, some rules. And what they do for us is that, well, if you look at this contour, if I think of this blue curve as a contour, I could deform it to infinity and get 0. So that relates the EFT part to the UV part, high energy part. So I get a relation between EFT physics and heavier stuff above the cutoff. And these integrals converge when you put enough powers of energy downstairs because of the boundedness of this amplitude. Okay. The only thing we're going to be using here is that, so this EFT, on the left here are the couplings we try to bound. On the right, you have a lot of unknown couplings. We don't know anything about the amplitude at high energy, but we know that its imaginary part is a sum of positive coefficients times Legendre polynomials. And we're just going to be using the positivity of these unknowns. It's very weak. We just use that. The amplitude itself, the imaginary part, it's not even positive itself. In the physical region we're looking at, like physical scattering, fixed angle, or some momentum transfer, the Legendre polynomials are oscillatory. So the amplitude is not positive, but it's a sum of Legendre polynomials with positive coefficients. That's all we're going to use. These unknowns are positive. And then the goal is to try to write some combinations of EFT couplings as positive sums. And we get some interesting inequalities. Okay, so here's a warm-up. I'm going to describe how we did this. I'm going to go a bit fast on this. So this is a project we did a year and a half ago about. So it's a warm-up about case without gravity. That's an interesting example. So suppose you have a scalar or singular real scalar field. And okay, these are the relevant interactions in 4D. And then you imagine you add a bunch of higher derivative corrections. Again, the idea is to not parameterize Lagrangian, but parameterize the scattering amplitude they lead to. These are very easy to enumerate. You just list symmetric polynomials. And we're going to be assuming that we have an effective field theory. So the thing with scattering must be much lighter than the cutoff. So we're just going to take it massless. Doesn't change anything. And the goal will be, in this problem, will be to bound these higher derivative corrections. And our framework basically, with this dispersive sum rule that I showed, they give sum rules of this type. They give, for each power of S, basically, you get a sum rule. And it looks like this. So the first one for second power, you get a series of EFT coupling is equal to some sum over positive unknowns. This bracket means sum over positive unknowns times these special functions. And all the unknowns exist above the cutoff. And okay, I said that you should be integrating this against normalizable wave packets, but let's be lazy and just expand in the forward limit, which is not normalizable, but let's do it. If you do this, you get very simple sum rules that have been extensively discussed in the literature. Like you get some rule that express this first coefficient in terms of the forward limit of this, which is just this. So obviously this implies that this thing is positive. So that's interesting, right? So some sign constraints on this thing. We also look at the next guy, and then you can write it as this average, this is spin square, and spin Casimir. And clearly this, once you write this coefficient, so G3 means that's 3 powers of Mannestam's, or 6 derivative. This G3, obviously, once you write it like this, and since all the unknowns are above the cutoff M, it's upper bounded by the leading one. The leading one has to be positive, and then all the other ones are bounded by it. So you very quickly reach those conclusions. There's a bit of a subtlety which was only resolved in the last 2 years, which is that here it seems like you just get one side. For some things, you only get one-sided bounds, because then how do you bound the spin of the exchange particles? Because in the UV, you can have particles of any spin. If the UV completion is some strongly coupled physics, how do you bound this gadget, the spin of the exchange particles? It seems like you could make this higher derivative correction arbitrarily negative by exchanging a particle of state 1,000,000, a spin 1,000,000. And it turned out you can't do that. That's the thing which was realized in his papers, is that the basic reason is that when you look at these sum rules, it turns out that there are more than one ways to measure the same coupling. That's related to crossing symmetry. And that tells you that the unknowns are not completely unknowns. Some averages have to give 0. So there's a constraint on UV spectral density coming from crossing symmetry of light physics. It's really a constraint on like AV couplings. Not really, I would not call that a UV-IR mixing. But anyway, there's some constraints. And if you stare at these constraints, you can quickly convince yourself that it prevents states with large spin from contributing too much. It's balancing large spins against small spins. That's the way you can get 0. And if you manipulate this, you get a bound like this, which shows that as far as this kind of sum rules go, the spin over M, which is like the impact parameter of the process, is basically bounded by the cutoff. Sorry, this should be capital M on this left-hand side because I put it outside. So as far as sum rules are concerned, heavy states with large spin or large size can't make a significant contribution. Sum rules are always dominated by small objects, which may not be surprising, but it kind of it plugs an important possible loophole, which is, in many theories, we're not saying that large objects don't exist. In theory of gravity, we definitely have large black holes. Maybe you have long strings. Big objects can exist. But what crossing symmetry at low energies imply is that big objects never dominate some rules. As far as all these sum rules go, you can assume that all objects have size the cutoff. And that's basically because all the sum rules which converge have inverse power of the mass of the state downstairs, so that it's just dominated by scales, by states with energy close to the cutoff and size not close to the cutoff as well. So you can't, big objects can exist, but they can never dominate these sum rules. And once you absorb this lesson, then it becomes obvious you can get two-sided bounds on any EFT coefficient. So this is at least our ratio of coefficients. So once you've bounded this, so G2 is the equation of the four derivative guy, which has to be positive. Once you've, in terms of it, everything else has two-sided bounds. And these bounds, no, they don't grow. So it's compatible with the geometric series, basically, as you would guess from anything outer particles. And there's a lot of analytic understanding of these shapes. I will not go through this, but there's a lot of progress in using these constraints. Today I want to talk about gravity. I want to show results about gravity, not scalars. The first step was done in this nice paper last spring, where they analyze this kind of sum rules for gravity, and the novelty, well, not an interesting thing they did is that they compare the allowed space. This is from some coupling we'll define later. They analyze the bound that they get using this method, which is the dark line at the bottom, with the space that could actually realize by known theories. And they found this, well, striking result that the bounds seem very conservative. It's not nearly saturated by any theory. So they propose some extra assumption which will reduce this bound, but the things you prove using on the causality and unitarity seem much weaker than the observed data. So we're going to comment on that in a few minutes. Oops, and I'm going to skip this slide. So we can also look at scalar plus graviton, and scalar which exchange gravitons in the paper, but I will skip this. So let's scalar gravitons. Turns out to be easier than scalar exchanging gravitons. So let's scatter gravitons. Result from a paper a few weeks ago. The basic point is that when you apply this framework of dispersion relations and analyticity of amplitude, when you apply it to spinning particles, you get stronger results. And that is just because the thing we're trying to bound, so if you scatter, for example, particles of helicity plus, graviton of plus, minus, minus, plus, you need some factor which depends on the helicity of the particles that's factored out times an amplitude, which the amplitude is going to be polynomial itself. So we're trying to bound these polynomials, but they multiply something which grows with energy, with a huge power. And this is related to the fact that you need, by gauge invariance, you need many derivatives, and your all the contact interactions have many, many derivatives. It's related to that. But there's this overall factor that you can pull out. And this factor grows with energy, at least in some channel. So, and this growth means that you don't actually need to do, you don't need, normally the thing that's converged were like twice subtracted dispersion relations. But for gravity, you don't even need subtractions. You can even anti-subtract and integrate a polynomial against this thing in the square bracket and still get something that's a convergent integral where you can drop the arc at infinity. So because the amplitude is bounded, the thing in the bracket is like super bounded. This is called superconvergence, and this is awesome. The reason it's awesome is that this superconvergence sum rule, which are integrals involving polynomials, they automatically kill all these garbage contact terms. And they just give you a finite sum of the cubic interactions. So you get a finite sum of stuff, that's an exact left-hand side of these sum rules, is equal to some integral over AV states. And here I wrote it in full, it's a bit messy, but it's integral over AV states of some positive unknowns times The legend polynomials for spinning particles are called Wigner D functions, but yeah, there's just some known special functions. And so we have some rules of this type. And then, okay, we could manipulate these sum rules to derive things like the argument by CEMZ that I mentioned earlier in this talk. But actually, we can do something much simpler. The trick is if you just find one magic combination of these, like you integrate against some wave function of P, if you can find only one combination of these, which writes gravity as a positive sum, then you can use this magic combination to dominate every other coupling. And this turns out that this magic combination exists. So what you get are bounds like this. Could say more about this kind of problem. It's a bit. Sorry, I did not define the problem, but maybe state it in a few seconds. The following mathematical problem is relevant. We need functions that have compact support in momentum space, because the momentum on the left have to be below the cutoff, and that are positive in impact parameter space. That's kind of like the right-hand side. So compact support in momentum and positive in impact. We need such functions. Turns out they exist. I don't know a general theory of these functions, how to make them, but like we just make some giant polynomial ansatz and ask the computer to find positive combinations, and we find them. It's a very interesting mathematical problem. So compact support in momentum, because the momentum has to be below the cutoff, and positive in impact parameters. So using these wave functions, we prove these bounds. This kind of bounds, and these bounds, they show that out of these higher derivative corrections, they're bounded by gravity. That's TNF. And in 4 dimensions, there are infrared log divergence that I will not, they force on us. It's really hard. We don't know what to do about them, but I'm happy to live with the log. You know, log of infinity can't really be bigger than 100. So, and if you take the size of the universe, Planck units. So, yeah, it would be nice to improve that log, but I'm not worried about it at all. So our message is this. If you write your action in terms of rescaled couplings of this type, these couplings can't be bigger than order 1 in terms of mass of I, right? So the interactions have to be suppressed by the higher spin particles. So the higher spin mass. And yeah, if they exceeded that, you will have a violation of causality. And the actual numbers, the order 1 numbers, are in this plot. And we actually make like, we prefer to make 2D exclusion plots rather than just range, but I can read off the range. And okay, we're going to briefly mention on when we do this systematic analysis, including these more sum rules. This is a plot that is meant to be analogous to the one a few slides ago, where you when you compare it's the same 2 couplings as discussed a few slides ago from this from like higher derivative corrections, like a bunch of derivative D4 R4, and then you can compare the results you get to known theories, and string theory lies on. We get string theory lies inside this allowed region. It's not that far from the corner, but it's not at the corner. It's a bit, yeah. If string theory were at the corner, we could say that like we could use the way this bootstrap works is that when the theory lives at the corner, like the 3D Ising model lives at the corner of the allowed space. When the theory lives at the corner, you can uniquely find its spectrum. That's very powerful. Here, just close the corner, so we don't really learn anything about string theory from this method, and like various things that don't look at all like string theory are allowed. It's just what you get from loops of the states. But yeah, the region is not saturated by known theories, but it's also not, there's not so much of a gap, I think, between the gap between what we understand and what is realized is not so which as it was. And just to put it differently in terms of projecting into the ratio, which is like the slope in this plot, the ratio of these two couplings, then it was a previous bound, and now this is the improved bound, which is pretty much like the conjecture bound that they have. So yeah, this is starting to converge gradually to the space of theories. But I think to really converge fully, we're going to need to get rid of this log, and that's really an important open question. Like repeat this analysis using some, infrared finite dress amplitude or something. But this is beyond what we can do now. So let me conclude with brief comments on what does it mean. So what does it mean? So we've shown that if you have an action of this form, like if you suppose you were to measure higher derivative correction, you could write it in this form. And naive effective field theorists will look at this and say, well, probably there's some new physics at the scale m, because that's where the derivative expansion breaks down, right? You naively guess that. But their friend could say something else. Their friend could say, well, you could also get a term of the size by integrating a particle that's much heavier than m, and right, it doesn't have to be a particle at the scale m. And just to explain this, what's remarkable about the bounds we get is that they come from particles that couple to two gravitons with Planck suppressed coupling. Coupling that's comparable in size with the 3-graviton coupling. But someone could have said the skeptical friend has in mind a picture where the gravitons can couple strongly to the higher spin particle with coupling that are order 1 and units of h bar. And what we've shown is that we rule out the second option. The coupling between two gravitons and anything cannot exceed the 3-graviton coupling, which is Planck suppressed. It's impossible. Gravitons cannot interact strongly below the Planck scale. It's impossible. They cannot interact strongly with anything. That's what we've shown. And the way we've shown it, if I go back, is by using this superconvergent sum rule that prove that gravity is attractive and bound and dominate every other coupling. So once you have a sum rule that dominates, so we can dominate all other couplings by gravity. So we rule out that option. That's our main result. It's nice that it agrees with the naive interpretation, but I think it's non-trivial. And the last comment is like, what do we know about these higher spin particles? And well, so we've shown that if you see a modification to Einstein gravity, higher derivative term, there has to be higher spin particle with gravity couples too. Now we can ask, well, does this higher spin particle has to couple to the standard model, or can we hide it? I think I would like to argue that it seems hard to hide it. No, in models like string theory, you cannot hide it. Like as soon as you have string states, everything is string. But you can imagine, you can try to look for qualitatively different scenarios. And we kind of speculate a bit around that. Ultimately, the thing to do is to constrain the couplings of these higher spins to matter. And that's going to be a whole other project. But yeah, assuming that this particle exists, we can ask, but suppose they couple to the standard model, could we bound them? And okay, if it was in any scenario that looks kind of like string theory, or if the spin-4 particles have to couple with gravitational strength, which give you a cross section with just 1/Planck square, then basically you will have seen them at LHC. You would have seen missing energy and deciding a gluon there so you can trigger the jet. But like if you scatter quarks and you can get a gluon out, and so any spin-4 particle that has gravitational coupling to matter, you would just have seen, unless it's less than the MEV or something. Even though there's a Planck suppression, the point is that higher spin particles, when you write a vertex, you need a lot of derivatives. So you get these cross sections which grow with some ridiculous power of energy. So even though it's Planck suppressed, if the cutoff is much less than a TV, the energy growth kills it. So it's very hard to hide higher spin particles if they have any kind of couplings to standard model. However, there's still a scenario that could not hide. So if these higher spin particles don't necessarily have to, well, if they don't have to couple the standard model, the only way you produce them is by changing your graviton and then having this coupling, which is the only thing that we know is there. But depending on the helicity of these, depending on which tensor structure you put there, it could be that you only have a cross section of this type. Now it still grows fast with energy, but it's less. We argue. I'm not going to give numbers here, but we argue in the paper that it will still be hard to have a correction that's big enough to matter in astrophysics. From even if in minimal scenario particle, you only basically there's a tension between the thing that we know from LHC, from colliders, and the things we're looking in the sky. It seems that one is excluding the other. It's very hard to hide something from a standard model because as soon as you couple the gravity, you have at least a process like this. What happened in string theory is that this process doesn't grow like energy like this. That's because you have other particles which couple directly to the standard model. But if you have those, then you're back to the process on the left. And we try to argue that any ways of softening this amplitude to make it less observable and reduce this energy growth would create other channel that makes it easier to see anyway. It seems really hard to hide these higher spin particles from colliders. But this is something that should be analyzed carefully in the future. But at least like order of magnitude level, it seems hard to hide them. So what would be conclusion? Right. So if we see experimentally some small departure of gravity from expectation of GR, I'm quoting a very small number that's basically because of this fact that the scale of the higher spin particle is much smaller than the size of the object. Well, there can be many explanations. Maybe it's new like scalars or vector boson exchanges, thing that people call fifth forces. That could be a valid explanation. It could be other conventional new physics or new particles. And this, I think, is something we're basically ruling out, or that we can try to rule out by this type of stuff. It could be an experimental error. Or finally, it could be that experiments would have revealed that causality doesn't work like the way we thought. But yeah, we're making progress on like the question of like what exactly are we testing. So there's a lot of open questions. So clearly, now that we know that these higher spin particles have to exist, we want to understand how they couple to our stuff. But they have to exist if there's a modification to GR. We neglected the loop correction. That makes sense because we're doing scattering below the Planck scale. But we expect it's small compared to the effects we look, but it should be checked. These IR logs are annoying and clearly they indicate that we should be able to get improved bounds in the future that don't have logs. One can play this game in higher space-time dimensions. And maybe somehow we get closer and closer to string theory. I don't know. So there's that's important things to do. And yeah, that's the last bullet point is the other question I mentioned in the beginning. And instead of looking at the maximal departure from Einstein, and look for the minimal departure. More should be, yeah. So there's a lot of questions involving gravity and causality. Yeah. So thank you.
Thank you, Simon, for the very nice talk. Are there any questions? Yeah, Ricardo, go ahead.
Yeah, I have two questions. So about these logs, like you should expect the curvature correction to drop off like at very large distances, right? So I mean, at least for these R cube R to the 4. So I I guess what I mean is that if you remove the log from the conal phase, like that should be it, right?
Yeah, but the thing is that
I don't see the problem. Maybe not a comfortable.
No. This is a very important point, because it's about what are we bounding, and I think in this CNZ type argument it's a bit clearer. What we are bounding from this dispersion relation argument is like the total amplitude has to be positive. That's Einstein plus correction has to be positive. And that's why we end up making statement that the correction have to be dominated by Einstein in some limit. We're not saying that if you subtract Einstein, you still have something positive.
Okay.
And we're not saying anything about the sign of that. Maybe there are ways to make statement about this. People have tried to make, there's like a dozen different versions of causality constraints that people use in the literature. Some of these versions involve subtracting Einstein and just looking at the corrections.
What I mean is that, like, as you said, like there should be, Newton's law at very, very large distances for these theories or not. Yeah. I guess you're looking at corrections, so that you have to check whether there should be corrections of this very IR dynamics in the sense.
Yeah. And the thing that's a bit frustrating is that you get this log, even if we're imagining we scatter wave packets that are focused and they're going to small impact parameters. But the log comes not from the scattering at small impact parameters, the log comes from sending in the particles to infinity.
No, exactly.
It comes from the travel from infinity to the scattering point. The interaction.
No, what I mean is the usual dressing that people use in perturbative quantum gravity just removes the 1/epsilon piece in the conal phase, essentially.
Yeah, I agree. But then the problem is that we don't know that the thing you're left with satisfy positivity constraints.
Yeah.
Because if you can show that this, it's beautiful to define this dressed amplitudes that are finite, but if you cannot tell me what S dagger S equal 1 becomes for this, if you can show me what unitarity means for these things, I cannot use them. This has been on my wish list, like my Christmas wish list for a few Christmas. I want I want to know what unitarity means for these dressed amplitudes.
No, I think, I had this discussion with Sasha as well, like when you use unitarity and something is IR divergent, right? So you go...
As soon as you start subtracting things, there's a danger that what you're left with, you over subtract it and it's no longer positive.
Yeah.
Can I ask one more question?
Yes. Sorry, can I just finish, like, just one more, like, for the FFR theory, if you're able to bound something like the energy emitted, like that should contribute like the zero mode of the scalar, right? Instead of bounding this. The stress tensor receives contribution at infinity, so its own shell, from the zero mode in FFR.
Yeah, I'm not sure what that means for a scattering experiment. Sorry.
If you're able to bound the energy like that you receive, right?
Like radiated?
Yeah.
Yeah, okay, that sounds interesting. But yeah, this will be, for us, this will be looking at some IR point amplitude involving scattering of gravitons and possible... is energy because you're radiating scalar physically? Or what?
No, it's just that when usually you define the energy at infinity, right? The higher curvature correction do not contribute to the stress tensor at infinity, but the zero mode contributes in FFR. It's something particular of FFR, and it does give a contribution. So then you can bound something on shell, because you can consider the energy emitted, and that one will have. You can consider that from amplitudes, I guess.
Okay, we can talk more after. Yeah, I don't immediately see, because for me, I'm assuming Lorentz invariant vacuum, so I'm just defining the vacuum energy to be zero, and then I can excite gravitons. But if you have a way of bounding the amount of energy that's radiated, this sounds like something that will show up for us in like an IR point amplitude, maybe.
Well, you have to modify, I guess, the dispersion relation some way. Well, anyway, okay.
Yeah. Other questions?
Thanks.
Oh, thanks.
Samson, go ahead.
Oh, yes. So if I now kind of start coming from the answer, which I know is correct,
like string theory,
I want to find why string theory in this way will require infinitely many higher spin particles.
Yeah.
Right. That's a drastic difference. Right? Infinitely many
No. This is This is actually easy. So the fact that you need infinitely many is sorry. Let me just find a place. But it's I mean, we show that there has to exist a particle of spin 4 and higher, but actually you can get a lot of some rules. It comes from let me show you.
You mean that
It comes from but as soon as you have inequality that looks like this, so if you stare at this inequality, if you look at this sum rule here, it's not so obvious, but when you plug in numbers, you find that this has like, well, positive sign at large spin, but negative sign on spin 2. So this sum rule here is telling you that you have your spin 2 state, you need state of spin 4 and higher. But then you can write you can find variation of some rule which will that if you have a spin 4 particle, you need one of spin 6. If you have a spin 6, you need
right. I understand. So you're saying from this it follows that the moment I add anything higher spins than 2,
you need a full power.
I will have to add all of them.
Yeah, you need all of them. So this is very clear. The thing that is not clear is that the thing you add have to look like string states, because a simple way to add higher particles is like if you have a 2-particle state from something in a loop. For us, that counts as a state.
Yes, I understand. So that means actually that you can see that the amplitudes have dual resonance picture.
Yeah, but they don't have to be narrow resonance. To show that there has to be string theory, you have to show that each of these resonances is narrow.
Right, and also their spectrum is very specific.
Yeah, and then
so what is missing basically is to narrow down to this state. So what we discovered this way is that it has to be infinitely many higher spins. It has to be they are massive, and now question is only if the spectrum is exactly the only possible one is the one that you get from dual resonance model with string spectrum.
Yeah, and
is that true?
Yeah, and you know, I think it's a sort of question that can be addressed in steps, because but one thing you can ask is typically when you have a cusp in these plots, there's a unique spectrum that lives there. It's not so obvious probably, but there's some statement about convex optimization. But when there's a theory that maximizes a bound, it's kind of a unique theory. So one question you can ask is, what is the spectrum of this theory at this cusp here at the top right? And well, if this cusp has been string theory, you could have hoped that you would discover string theory from that.
Right. I do actually remember from 40 years ago, childhood, that there was a statement that if you want to have the poles, when you sum over intermediate states, we want to have poles same as in S channel as a T channel and so on, then the spectrum of the massive states inside the whatever sum has to be very specific. You don't get proper poles in ST and U channels that you need. I never followed in details, but I thought that was fixing the spectrum.
I think there are a lot of arguments, variation of the arguments that if you assume that you have poles and not cuts or resonance, but then you have to have string theory. But there are variations actually. There are two that are unitary and they have nonlinear rigid trajectories. There are counterexamples to.
There are counterexamples. Okay.
There are counterexamples.
So those restrictions on ST and U channel having the properties as Venetian amplitude has is a very strong restriction. Only question is to find the principle in your way of looking on things. What does it correspond?
Yeah.
Causality, unitarity is clear, but there are some other things probably.
Yeah. We don't know what else to add. But I think, I mean, some of the direction of, I mean, I agree with these. I mean, I think it's a bit premature to say that something else is needed. I think it's important to think about what else can we add to this business, but.
Sorry. But the reason what I was saying about something else was that if we want to narrow it down to, that's only, I'm just looking on one point here, which string theory. String theory has huge amount of symmetries. that we have not discovered yet because we don't know proper formulation of it. So there is something very unique in string theory, right? I mean, people who work in string field theory, they say that symmetries of string theory have not been yet discovered, only corners like S duality, T duality, whatever. But in general, there are a bunch of them. And without knowing what they are, it will be hard to narrow down to it unless there is some substantial luck that you just hit with one or two principles that it singles out string theory. So basically what I feel is that it always will be this kind of whatever land of opportunities there.
It's possible. I'm a bit, I'm actually agnostic about the option is that, I mean, to me, it's not so important that the only point in the land would be string theory because, I mean, as far as our constraints go, they're a bit linear. So you could take a linear combination of two different string theories and it will still be allowed. So you're never going to get just a point. But
well, that's a different background. No, that's a different background of the same string theory. So string theory has many backgrounds. You can build it by multiplying things and so on. But as you know, any conformal field theory in 2 dimensions is a background of string theory. So if we would have background independent approach, then it's right. But you are in one background, which is particular flat space, Lorentz, whatever variant.
But I would say that before concluding that we really need other principles, I think I would like to see these plots in higher dimensions. Because you know there are many when we reduce to 4 dimensions, there's many there's a lot more options than.
Yes, but this is all 4-dimensional. Yes, I agree.
This is a 4-dimensional plot. So I mean, until I see it, and okay, I don't know when it's going to be available, but until I see the higher dimensional version of this plot, I will not jump to conclusion about needing. I'm really agnostic about what would come up to this point.
So this is more like people in effective field theory do, let's say, put a neutrality condition and suddenly discovers that in pi meson Lagrangian at some energies there has to be rho meson, otherwise there is violation, and then they go in hard and so on. So this way, in effective field theory, they don't go very far, but they still.
But one of the main point is that. Yeah, for pions, you don't go very far, and I agree with this. But I think for gravitons, we go further because the spin of the gravitons helps a lot.
Yeah.
I think.
Thank you.
I think
yes,
somehow, I think this constraint somehow this dispersion relation that's been used in QCD for like 50 years, but I think what they really meant to be used for is gravity.
Except in that case, we kind of eventually know that we can do the loop correction. This is all before that, right?
Yeah, but in gravity, there's actually a reason to neglect that because if the couplings are Planck suppressed, the loops are actually small.
That is correct, unless
it's actually justified to do it.
Yes, that is true until you said, and you said yourself that there is a condition there which requires infinitely many massive states with higher spin, which means that, forget about, if you have infinity times 0 and so on, I would not much trust this kind of suppression because you have infinite sum.
No, the sum over spins is not a problem because the sum over spin is, it's like the integral over impact parameters. It's we regulate it by studying wave packets that are normalizable in impact parameters. That automatically.
I meant sum over spins. Sorry, I meant sum over intermediate states of higher spins with masses when there is a suppression of each term, but there are infinitely many of them, and they can contribute.
The whole sum is still suppressed because when you scatter a normalized wave packet, you cannot have a divergent cross section.
So how do you get then the pole in the T-channel?
Well, we don't see a pole because we integrate against a normalizable function of T.
Right. You don't see the pole.
You don't see the pole.
then you cannot have dual resonance.
No, but we don't see the pole, but we can see the coefficient of the pole very accurately without seeing that it's a pole.
Oh. Yeah, well, there.
It's there's a bit of, yeah, you have to get used to like what we, the constraints that we have to satisfy, but these constraints allow us to do interesting, tough experiments. Yeah.
Thanks.
Yeah, thanks for those are good questions.
Hey, thanks. Are there any other questions? Okay, if not, then let's thank Simon again for the very nice talk. Thanks a lot, Simon.
Thank you.